GM, welcome to another episode of The Rollup. Today we have the pleasure of speaking with Brett and Cecilia of Gwyneth. And Gwyneth is a based rollup incubated by Taiko, which is using the based boosted contestable rollup stack out of Taiko. We discuss the mechanism design for Gwyneth and discuss some of the trade-offs for based rollups in general. Hope you enjoyed today's video. Before we get into it, a word from our sponsors. Enjoy. Cartesia is your home for app-specific rollups. At the forefront of developing new tools and platforms that enhance the capabilities of blockchain technology, Cartesia enables applications that are flexible and built to scale. Build on a full Linux environment and use traditional software libraries, but in blockchain development. Go to cartesia.io, that's cartesia.io, to learn more about building your own app chain today. Mantle is a layer 2 blockchain with one of the biggest on-chain treasuries in all of crypto, and they have a 100-day campaign called Metamorphosis live now. What this is it is a campaign for their liquid staked ETH token, METH, as well as their upcoming liquid restaking token, CMETH, where you can utilize this token on the Mantle network in a variety of different apps, some of your favorite restaking protocols and DeFi protocols, and earn yields in the form of powder, which will eventually be turning into a governance token. Mantle's been around for a while. We like them because they use their own form of eigenDA. They have a good ecosystem and they're growing. So check out this 100-day Metamorphosis campaign and hope you guys enjoy the rest of this video.
What's going on? Welcome back to The Rollup. I'm standing desk in NYC. First podcast ever on a standing desk. I think the size of the desk is a little too big, but then I have this box for my camera. So just trying to figure it out here, but I'm feeling pretty based right now. And I know Brett is as well. And we have a new guest, Cecilia. So looking forward to that. Brett, welcome back. Rob, GM. And yeah, man, we're going to put some based rollup educational content together today.
Yeah, thanks for having us back. And well, I guess it's kind of like a nice evolution, I think, from my previous presentation. Although like some parts even from the presentation are exactly the same, but we'll give some updates and the evolution that the design has gone through, and also like the different priorities than I guess like last time. Because there's some extra cool shit that we can actually do now. So yeah, it'll be great to kind of like explain and also like let people kind of like learn like what we're actually doing, and hopefully they agree this is actually pretty cool and a useful solution.
Hell yeah! And Cecilia, would love a quick intro because it's your first time on the show, and then we can jump in.
So hi everyone, my name is Cecilia. I'm a ZK developer at Taiko, now at Gwyneth. And these days I've been working on like base pre-confirmation protocol design and also some of the client code. Just helping out Brecht in general. So nice to see you guys.
Welcome. Yeah, very excited to learn more about base pre-confirmations and Gwyneth in general. Yeah, why don't you guys have a whole presentation prepared, so feel free to jump right in.
Right. Okay, so let's start with like what actually Gwyneth is, I guess. Gwyneth, I have to make sure that I actually also pronounce this correctly, but it is Gwyneth is the pronunciation. So yeah, let's just talk about like, okay, what makes like Gwyneth kind of special, or kind of like what are the core features. So if you go to the next slide, Cecilia.
Okay,
so what is Gwyneth? It's still like Taiko, still a boost, like a based rollup, of course. And I guess the new thing there will also like be like based pre-confirmations, because obviously one of the downsides of being based is kind of like the longer confirmation time for users, and also kind of like the less kind of like lower efficiency also because of that reason. So kind of like one thing that we want to make sure we get right this time as well is having like high efficiency of like how blocks are being proposed, but also from like the user perspective where, yeah, they kind of like have like very fast confirmation times if they actually do a transaction on Gwyneth. So yeah, that's kind of like a big thing. Although this presentation will mostly not go about, will be about like pre-confirmations, but if there's more questions about it, then I'm very glad to ask it. But yeah, most of the presentation will be kind of like about like how we kind of like do the horizontal scaling part using Boosted Rollup still, but also combined now with like synchronous composability between all the different layers. So previously the focus was mostly on like synchronous composability between the L2s themselves within Gwyneth. But now we also put like a lot of focus on actually making it possible to do synchronous composability with the L1 as well. And so the reason this wasn't like a focus before is because doing synchronous composability with the L1 is kind of like a not easy, and you kind of like have to have the necessary infrastructure to even be able to do it. But I guess that's something we will explain like in one of the later slides as well. And then, yeah, obviously still a booster rollup. So we have like the extra functionality to be able to cheaply access like state on the L1 or and other L2s as well. But like, I guess the L1 part is kind of like the most interesting one. And then, yeah, the other thing to also make it possible to do synchronous composability with L1 is kind of like real-time proving, or at least like close to real-time proving, something like sub 12 seconds, the L1 block times. And yeah, one other thing that's also kind of like important for that is we only need like real-time proving, but the finalization time of the proof itself also kind of like needs to be directly. So when we post the proof on chain, it has to be accepted directly to be able to do the synchronous composability with L1. And to make sure that that is actually like a secure and to have like enough confidence in this, we also have to use like a multi-prover to be able to do that. So we don't just have like the security relies on like a single proof or like even one single type of proof. We kind of like want to have like some diversity there, doing like the multiple nodes implementation and that kind of like stuff. So yeah, that's in a nutshell what the Gwyneth is trying to do, and what we'll try to explain more in detail in the next couple of slides.
So currently in the ecosystem, we have like a lot of L2s. And obviously that will introduce fragmented liquidity, right? And also I feel like people are running out of thesis for launching more L2s, so that we come to this app chain thesis, which is good, but it doesn't stop liquidity being fragmented furthermore. And we kind of need a solution to stop diluting the liquidity, also stop deteriorating the user experience. Because like bridging from different L2s, even given the app chains that you're using, is kind of painful. That's the ecosystem perspective. And for a technical perspective, we think that ideally we can have a single chain. At least from a user experience, everything should be seen like a single chain. But the fact is, a single chain can't scale that much because of high congestion. Like if you have one chain following the 1559 paradigm, you have like very high congestion fee, and results in a very high base fee that the user will see. And also like for the current L1, the block time is capped at 12 seconds because in order to maintain like the security assumption that we want to have for L1, given the large amount of validator, you do have a lot of BLS signatures to aggregate, and also the consensus itself, and just to sync the state. And that's like 12-second is a very realistic cap for a large blockchain like Ethereum. So a single chain is like literally not possible for the user experience that we want to aim for. So we sort of want to break it up to more chain, but hopefully for the user, it still look like one chain. So that's the goal of Gwyneth.
Yeah, we've been talking a lot about that here. Like, just like you just can't scale a single state machine. Mm-hmm. And the bet of this modular thesis, if you will, or like this kind of roll-up centric roadmap, is that we can scale app chains and rollups and put them together via what you guys are going to are US-based rollup composability, what others are saying intents, what others are going to say shared sequencing and coordinated block building, or just basic transport layers, and do such in a way that is also abstracted away via some orchestration or some wallet abstraction partners on the user level. And so that's like the bet. And I put out a tweet. I was like, I think the bet is that if we can't do it, then we struggle to kind of fulfill the vision of like what we think is achievable for maximum scale. But if we can achieve that and then go further from there into different ZK and base designs, etc., then I think I wrote, and I think this is how I feel, that like the end game or the result is almost like unimaginable. So I just think that we're on the same page there, and I just wanted to kind of further reinforce the way that you guys are thinking about this. But I'm excited to get school and technicals, so let's do it.
Yeah, let's do it. Okay, Brett.
Right. So yeah, I guess I guess in the end, the only thing that really matters is the UX or like whatever users see, but we go into the technicals because that's what we actually do. So okay, let's start from like the current like well I guess it's still the current kind of like state of things. So you have like a single like isolated rollups, and they have like their own kind of like way to kind of like deposit and withdraw. And basically they're like just like fragmented, isolated kind of like islands. Everything that is happening on this L2 only happening on this L2. You can't directly interact with the L1. You cannot directly interact with any other L2s. So that's not a great experience, especially if you have like hundreds of these. So not good enough. Let's go to the next step where we actually introduce like multiple L2s. So this is kind of like the same thing, but like with multiple L2s here. So each L2 has like their own bridge, and if they all have like their own bridge, then moving funds from like one roll up to the other has to go through this L1 bridge, this bridge that is on L1, which is very expensive to begin with, and also not a great user experience because people have to wait until kind of like the L2 kind of like finalizes, which could be like a couple of hours until up to like a week for like optimistic rollups. So this is not great, and there are solutions to kind of like get around this problem, but then they kind of like depend on like liquidity providers, which is not capital efficient, and also introduce like extra fees and things like that. So not still the status quo, but not a great solution. So how do we improve on this? It's kind of like this kind of like shared bridge kind of like design, which I guess is kind of like now the accepted kind of like solution to like how to actually do this. So instead of having each rollup have its own bridge, on the L1, you have like a shared bridge on the L1, which contains all the deposits for all the L2s kind of like combined. So that means that you don't have to go through the L1 again. Don't have to go through the L1 to kind of like move funds from one L2 to the other. You can just do some kind of like proof that you kind of like burn some kind of like funds on rollup A, and then you can mint them on rollup B. You don't have to touch the L1 at all. You just have to be able to prove that something happened on the other L2, and that's basically it. So this is pretty good solution. It's kind of like it's cheap because you don't only have to touch the two rollups that you're also like actually interested in. But it's still not ideal because it does have to happen like asynchronously. So you do have to have like two separate kind of like transactions, one to kind of like burn it, then one to kind of like mint it on the other rollup. And like the time frame to actually be able to mint the tokens on the other rollup depends on the finalization time of the source rollup. So if it's kind of like an optimistic rollup, then you can burn something on rollup A, but you will only be able to actually mint it again on the other rollup when the state has finalized on rollup A, which is kind of like a week. So this would be like a very, very slow method to do it. But for like ZK rollups, this would be kind of like acceptable depending on like how often the state is kind of like finalized. But still, it's asynchronous. People kind of like have to do these transactions in like multiple parts. There might be like a relayer that helps doing like the opposite transaction, but it's still kind of like pretty messy and not a great user experience. Also, it's kind of like not standardized, kind of like how this works. So depending on like what bridge or like what rollup you're on, the user experience might be like a pretty different.
Yeah, this is like reminds me not the synchronous necessarily, but the previous slide reminds me of like Superchain and Ag Layer and those types of designs, or at least like a similar thought process there. But I think like the big breakthrough that we're going to talk about here is kind of like the synchronous nature of based rollups as kind of like a big shelling point for the viability of them in the long term. So I'm kind of thinking about this as like there's like rollup clusters that we have right now. Like you've got like the super chain, like ZK Stack, and like Taiko has like its Gwyneth and Taiko, and perhaps other chains in the future. You got like Arbitrum. Now, these may fall into some of this asynchronous communication between these separate kind of like clusters, but I'm viewing this as like within the clusters, it's going to be synchronous, whether via coordinated block building or like base rollups or something like that. So, yeah, I kind of been slowly putting together a thesis on this, but definitely curious to understand what you guys think about that as well.
I think. Oh, You want to say something, Sia?
Yeah, I was gonna hit that like maybe we should like skip these like slides faster so that we could get to like the nitty gritties of synchronous block building. I think that would be the
Yeah.
part.
Fuck yeah.
Yeah,
Let's go.
see where you're going.
Oh, we're almost there. We're almost there. The next slide introduces the synchronous building aspect, about the synchronous aspect. So like how we actually see kind of like the synchronous composability working. So then, okay, we are there. We have like we still have like bridges in this kind of like scheme. But the bridges would basically be able to directly call each other to do the burning and minting. And so instead of having having the relying on like verifying workup proofs or kind of like any kind of like asynchronous proving process, we would just be able to prove all the L2s at the same time as they kind of like comment, but as transactions are actually executed. So you don't have to have like any specific like smart contracts kind of like specific functionality. You would simply be able to call in the other smart contract and kind of like, because the block would be proven together, you can indirectly kind of like prove all the interactions between them as well. So that's a good thing. But the one kind of like downside of this is, well, if you actually want this to be like scalable, and then if there's like lots of like these layer twos around, then to be able to verify that these transactions were actually executed correctly, you basically have to run a full node to be able to check that. And so, yeah, you can have like clusters or whatever you kind of like want to introduce, but ideally you would be able to just sync one L2 and be able to make sure that is L1, L2 that you're syncing is actually the correct state that you get from the L1. And so the easiest way and the most scalable way to do this is obviously validity proofs. And so what we will be doing is to directly have the validity proof available when the block is being proposed. And also the block that is being proposed is already like split up between the L2s, so that you only need to sync for like, you only need to actually execute the transactions that you are like interested in. So if you only want to sync with like rollup A, then on the on-chain data will provide you exactly with the data that's necessary to just sync rollup A, even if there's like cross-chain transactions going on. And so the data that's provided there, you can actually trust it because it will be validated with the validity proofs. So that's kind of like the easy way to do it, and also like the most scalable way to do it. But it does require on these real time proofs, or like close to real time proofs. And so that's kind of like where some of the challenges, I guess, come in, where currently the things that are available to do real-time proving is kind of like these DEs, SGX, whatever, and also kind of like ABS solutions where you simply have like all the people running nodes and then creating like a signature that the state is actually correct. But yeah, we are like a ZK rollup, so ideally, obviously, we believe that the ZK proofs are like the best proofs to actually verify these things. But for now, they actually cannot be used yet to generate these fast proofs, but to generate these proofs like fast enough. So that's kind of like the thing that currently is not available, but that we see as being available like pretty soon. There's like multiple people making some estimates there, like when this will be available. But let's say like roughly a year from now, it will probably be possible to also actually generate ZK proofs fast enough to also, yeah, generate like real-time proving or like close to real-time proving.
Oh, Brock, I'll go over the proof part later. Let's go to the next slide for now.
Okay. Okay, so we have the synchronous composability down. We have like a shared liquidity, like a bridge. So you don't have to touch the L1 if you don't have to. So pretty good solution. Still not like ideal, because if you kind of like want to increase scalability, then you have to deploy like multiple L2s, and these multiple L2s would basically be like, yeah, basically like clean slates. You don't have any existing states. If you want to do something on it, then you have to redeploy like smart contracts and all this kind of stuff. So that's kind of like where the kind of like the booster rollup functionality will come in, where you don't always have to like start from scratch. If you actually deploy like a new rollup, you basically inherit all the state from the L1, and users can directly use that new rollup to do all these kind of like functionality. And so you don't have to, yeah, recreate like ecosystems all the time.
Yeah,
So that's
real
kind of
quick, Grant, on that note, what's the latest on the booster? Like, is Gwyneth a booster rollup from like Taiko itself? Like, or Is that what you guys are calling a base boosted rollup? Is that what Gwyneth is technically, or no?
Not sure I completely understand the question, but I think yes,
Yeah.
as in the Gwyneth will be like will use booster rollup functionality, or like will have it, and also like combined with the base rollup. Yeah.
Well, I guess the name Booster is just Bragg just came up with that out of the blue.
Yeah, I remember that. That's what I'm saying.
That was
On one of our last. Okay. So this is how the booster design works here for
Right.
Gwyneth.
Yeah, I got it.
Okay.
So kind of like the new thing here is that compared to last time is you don't have to deploy like all the smart contracts on L1 because
Right.
that would be kind of like inefficient for certain use cases. So that's why there's some extra like smart contracts on the L2 side, because for example, if you for a user, if you want to have like a smart wallet, then you don't want to deploy that smart wallet to the L1, even though it has like benefits of doing that. It would be like very expensive to kind of like force users to do this if they actually want something like a specifically for themselves, and they are not really interested in having the functionality available on all the booster rollups. So yeah, it will be possible to just deploy a specific contract as well on like a single L2, and then you can just do all your transactions directly to all the L2s like normal. But yeah, for generalized applications, like if you want to have like a token contract, or you have like a real application like Uniswap or whatever, you would just still deploy it on the L1, because then you automatically scale your application across all the L2s. Yeah. So, well, I guess I already like said it, but yeah. So this system makes it possible to easily add more scalability to the system, so you don't have to like start from scratch. But
Yeah, horizontal scaling to the max. It's almost like
to the
sharding.
max.
I mean, so many of these roll-up designs that I see, these app chains and L2s and like this expansion of them, there's going to be so many, and like ephemeral roll-ups and all these different types. Like I just always come back to being like, damn it, we had the right idea with sharding. We just didn't realize that it was not going to be sharding the L1. It was going to be expanding horizontally by adding new state in the form of roll-ups, you know?
It's sharding, except in this case you do have like a shared kind of like storage room, and in the form of like the L1, and so being able to just not have like all the states sharded, but like having like this kind of like already like very well. But all the interesting data is mostly still on the L1. So having that available next to kind of like your own sharded storage, yeah, I think it's kind of like the thing that makes a lot of sense.
Okay, so I will go over like the details of what we actually mean, because I feel like Brack's explanation kind of goes everywhere. So like, let's start with like the semantics of cross-chain read and write. So currently on the left-hand side, you see this Merkle proof thing is basically how we read the L1 state or L2 state on these days, right? Today, right? If we want to prove to a chain where Alice has like $10 in L1, or Alice honestly deposit $10 in the bridge contract, we provide this Merkle proof. And that is like super asynchronous. That's like not synchronous composability at all. But like by saying that we add TE or ZK proof to the paradigm, it literally just means that like we run the whole execution of L1 or L2 of this like bridge smart contract on a node that has TE or ZK support. Right. So by the time where the execution is done, where Alice has deposited $10 in the bridge contract, we would have generated a real-time proof to the target chain, so that basically what we're doing is to prove the integrity of Alice deposit so that she can mint on L2. So the purpose of both sides of the diagrams are the same. It's just that currently the proof is being offered as a Merkle proof, which is also asynchronous. Like the proof is being supplied at the rolled up time. But now what we're trying to do is run everything within the same execution process, so that like the proofs is being seen in real time, where like a L1 and L2 node that are being run side by side can just like synchronously compose with each other. Yeah. So this is for a read. This is for cross-chain reading. For cross-chain writing, on the other hand, so let's say we have a Uniswap deploy on layer 2. Currently, what people are doing is at the rollup operation, where you update the rollup state, where you're actually updating is the state that are derived from the state root of the rollup. So let's say this Uniswap smart contract is on Arbitrum, and when Arbitrum rolled up to L1, the state root gets updated. So implicitly, it also updates the Uniswap pool status on Arbitrum through a state write to layer 1 Arbitrum state root. However, what we're trying to do right now on the right hand side is that when we're executing L2 transaction, which encapsulate a L1 call to the L1 Arbitrum smart contract, we will roll up the execution result of that call directly on L1. So by saying that we solve fragmented liquidity is the fact that you actually only have one Uniswap. There's no like two Uniswap on L1 and L2. There's only one Uniswap existing on L1, and then you kind of just directly modify the state via a delegate call, like a direct call to the Uniswap contract, as long as it inherit the boosted rollup interface. So yeah, and the call that are being initiated from L2 is like sort of enumerated at L2 execution in advance, and then by carrying out this enumeration on a TEE or some other like real-time proving solution, you also like generate the proof for that. So when you roll that up to L1 and your L1 smart contract execute the delegate call to the real Uniswap contract, the proof is also being verified. So this is what we mean by actual synchronous composability.
And Cecilia, if I have like a Uniswap instance on Arbitrum, Optimism, and Base,
Yeah.
then all of those end up getting aggregated when they change the state on the L1, and that's how the liquidity is synchronous and it's composable across those three environments, because you end up aggregating it when you change the L1 state.
Yes. So like you can still have Uniswap separately deploying on all of these chains, right? It's an implementation choice. Like Uniswap can be like, I only want one instance of my contract being deployed on the main chain, and then this contract inherit the booster rollup interface where for any subchain that carry out the execution of the Uniswap smart contract with a proof, can modify the state of the L1 Uniswap contract directly as long as the proofs are verified. So you're basically using L2 block space to execute L1 logic and
Right.
updating the L1 end result at rolled up time.
And then
Yeah.
and then the L1 is like a proof aggregator.
I will think that as a proof verifier, right? Or so that the proofs can be aggregated at the same time, right? If you have that many proofs, basically there's still like details regarding the block building. So you have to have like exclusive like write lock on the contract state of Uniswap, and that would be like implementation details that we may or may not have time to go over. So
Hopefully,
It's also like
yeah. Go ahead.
It's also important that you don't have to touch the L1 state if you don't have to, right? So if you don't want it, so it's kind of like up to the application to decide like how it's most efficient to kind of like split up the state. So you can have like a Uniswap pool on the L2, and you can actually write the state there directly. It would just be not directly shared between all the L2s and the L1 itself.
Cool. We'll try to stop interrupting you guys so that we can get to the block building part.
Sure. So Brax is gonna go over this simple example.
Okay. But people are interested in block building for some reason. Okay, so I'll keep it short. So we had this kind of like an easy kind of like example like how this actually would work. So for example, if the user has like a smart wallet on the L1, then this could contain like all the social recovery state there. But then this would still be like data there. And then on the L2 you would actually execute like a smart wallet transaction. This would be able to check like all the data that's on L1 to be able to say like, okay, I need like these two addresses to sign stuff. You would just be able to call like the L1 contract to kind of verify which signatures are required. And then the smart wallet on like the left L2 would also be able to directly just call the AMM smart contract on the other L2. So for the user, it's kind of like very seamless. There would be like only one transaction just to call the call into his own smart wallet. It would automatically check the data on L1. It would automatically call the other smart contract on the L2. And then these token transfers would just happen as they make sense. So this token smart contract would also be like deployed on the L1, which makes the token smart contract available on all the L2s. And then depending on where the balance is for the user, it could be on the same chain as the smart wallet. It could also be on another chain. It doesn't really matter. It just fetches the correct balance from like the chain that is storing the funds, swaps them on this AMM smart contract. So at that point, those two tokens do need to be on this specific chain. But then afterwards, again, you can just transfer the tokens to whatever chain L2 that you want. So that's kind of like very easy for the user, simple transaction as they are used to. Just like internally, it does like multiple cross-chain things. Let's skip over the contracts because there is some code there. And then yeah, shortly, like what a Gwyneth block looked like. So like there would be like each L2 would be its own thing, but there would be like a single like transaction list containing all the different transactions on all the different like L2s. So it's up to the builder to kind of like decide which transactions make sense and also which transaction he can actually build. Because if a builder wants to create execute a transaction that touches multiple chains, then the builder does need to have like all the state for these chains that are being touched. So depending on kind of like which chains are like the most popular or have like the most value, builders want to like pick and match which one they actually want to sync and so that they will be able to execute transactions that touch all of those chains. So yeah, it's kind of like up to builders to kind of like make sure this synchronous composability actually works in practice because they do have to sync the multiple chains. And then yeah, the builder builds a block. This kind of like super block is proven like in a single go, so only like one proof required to be able to prove any kind of like all the different L2 transactions, and then yeah, it should just work. Except that there's a kind of like a DDoS risk, as in like the builder, like if you do like a transaction and this transaction can touch like lots of like different chains, so the builder kind of like has to know for a transaction which chains will be touched. Otherwise, he might start executing a transaction and then see like, okay, I actually don't have like the necessary state to execute this transaction. So that's why the transaction format will also have to include like a list of all the chains that will be touched. And if the user kind of like is wrong, then the gas will still be used and the transaction will simply revert.
All right, so we're looking at some block building process more in depth, talking about some MEV here.
Right.
Let's go.
Yeah. So like let's start from like how does the MEV and PBS paradigm work nowadays on L1. So obviously we have this builder which has a lot of transactions in the mempool, and the builder would just pick whatever transaction that are profitable to form a block and submit this entire block through the PBS pipeline, which will have a validator and all that stuff, blah blah blah. And the builder gets revenue from any MEV plus tip, right? But what about if we add the base stuff in the paradigm? So we'll have L1 builder, which is also a base L2 builder, because that's the definition of base rollup. Your L1, L2 sequencer is also L1 sequencer, right? L1 validator. So in this case, then the builder's transaction pool, the mempool within the database will also have the access to L2 state. And also the L2 mempool itself. You have the L2 RPC endpoint, right? And in this case, the builder will just directly build the L2 blocks. You see this pink block over here, and this pink block is being built in the exact same way as L1 blocks, because you still receive MEV plus tip. Or if your L2 works differently, you might have other L2 fee accounting mechanism, but the whole L2 block is being packed in a rolled up operation, right? Like when you have like rolled up transaction proposal, every out of the entire batch is being batched in like a blob, in a transaction with 44 for blob or something. So this is how you rolled it up nowadays. And it actually works very nicely in a base sequencing mechanism. Yeah.
So just briefly here. So I understand how, let's say you have multiple base rollups, app chains, or just enter sort of, base rollup L2. They can settle atomically in the same L1 block because of the way that the sequencing happens, and that can allow them to have, basically like they can read each other's state and have really fluid cross domain interactions for asset transfers and messaging and things. But like you're giving away all of the transaction ordering, or at least from my understanding, you're giving away transaction ordering and sovereign sequencing as a form of revenue back to your sequencer and giving that to Ethereum L1 validators. And that doesn't seem like a great business model for app builders who want to accrue revenue for their block space demand that they have for their chain. How are you guys thinking about this?
Yeah, I totally see your argument, but actually it doesn't have to be that way, right? That's why I leave it open for the L2 sequencing protocol without specifying, okay, this is like an absolute anarchy that you can do anything. It's actually not the case. Like we can literally sell execution ticket on layer 2, right? If you're a sovereign app where you have block space that are profitable, you as a protocol can sell execution ticket to random block builder that wants to build your block. And we can also receive revenue from 1559 base fee. Because as you know, like people modify the fee accounting on Ethereum all the time. And you can also do that on layer 2 in any sort of manner that you want, such that you capture back some of the base fee that are about to burn, right? And in fact, that is how Taiko work currently. That we literally out of the base fee generated from Taiko, congestion is being transferred to our treasury. So
Cool.
You don't have to give up all of the revenue.
Understood. That's good to know. Is like as far as like the spectrum goes, I think a lot of people see things binary sometimes in technical designs, but it's often not. The other thing specifically with Gwyneth and Taiko's kind of booster designs with regards to the horizontal scalability, it seems like the design works better as more booster rollups come onto the system, because then you get this kind of expansion of composability across different chains with the same sequencing happening. And like you can get a lot more scale. Like all I'm saying is like if there's 3 booster rollups, it's like, okay, great, we can atomically compose amongst 3 different applications or ecosystems. But it was like 3,000, then it's like, oh, like this is a big problem right now in any sort of EVM centralized sequencer, or even like in a proposed decentralized sequencer manner. There's incentive issues and all these things. So like it really does seem like this design scales. The value in people's eyes, I think, will scale exponentially as the chains adopting the sequencing method grows. So I just wanted to also make that point and see kind of if you guys agree, which I assume that you do.
Vertex Edge is now live on Say Network. Say users can now trade 50 plus spot and perp markets with the unified order book liquidity of Vertex Edge across Arbitrum, Blast, Mantle, and Say. The next 6 weeks, 850,000 Say tokens will be up for grabs as trading rewards every single week, exclusively on Say. Join Vertex on Say Network now on Vertex Edge. That's vertexprotocol.com.
Covalent is solving the long-term data availability problem where a lot of the data availability providers today in the modular space, when you post data to them, they actually only hold that data for about 12 to 16 days. And then it's basically, it could go into an archive node, or oftentimes it's just kind of put away into the abyss. And what Covalent's trying to do is build this long-term data availability solution, which can plug into some of these modular data availability providers and provide this longer-term perpetual data solution. So what we try to think of this as is when you post transaction data onto Celestio or Veil or any of these modular DA solutions or even Ethereum, Covalent is able to provide a long-term data storage and data availability platform for that data after the time period. Blockchains are billboards, not databases, and we need these providers in the space to be able to kind of hold on to the long-term data that is provided from these providers and these blockchain state. This is where Covalent comes in. They just had a nice rebrand. Check them out on Twitter as well as the website. Thank you for being here. Hope you enjoy the rest of the show.
I was about to touch on that because I have many slides, but
sorry, I'm going to stop here.
But it's okay. But literally what you just mentioned is literally this situation that we're talking about, that I will be touching on. So I'll just jump ahead. So if we imagine we have like multiple layer 2s, right? We have this like pink layer 2 and the blue layer 2, where the builder choose to be the sequencer of both of these layer 2. Actually, the paradigm still work, right? Because you basically do the same thing for the other layer 2, where the transaction of different chain can actually synchronously compose with each other, because like they're basically in the same mempool, right? And if we have like atomic transaction where like a bundle can goes across the pink layer 2, the blue layer 2, and the gray layer 1, they can like literally be packaged with each other through the building paradigm that we're going to introduce. So like and also like different protocol, the protocol design is still like open for different layer 2, right? We can have the pink layer 2 selling execution ticket, and we can also have the blue layer 2 having a deterministic look ahead through AWS. So this system is like totally flexible. You can do whatever as long as the states are available for the builder to build. And the builder can also choose to exclude the layer 2 that he doesn't want a sequence for. Like the builder can just say like, I only have access to the pink layer 2, or I don't want the blue layer 2, or I just want to censor the blue layer 2, whatever, right? As long as you have the right RPC endpoint and you have the access to the mempool, the order flows, whatever, you can build for whatever you want. And I think this really introduced like a new MEV market where builder can really do like cross-chain atomic MEV in this paradigm.
Just want to also mention that like we do have to be careful about like adding like extra barriers to kind of like be able to synchronously compose between the L2s, because that's kind of like the main selling point is that it should be like easy and it should be like just like work out of the box. So if we have like multiple kind of like leader selections or like multiple like execution tickets for like the different L2s, then it's great for value capture, but we have to be also like be aware that this could actually increase like barriers and becoming like a builder, and also like decreasing like the chance that if you do like a cross-chain transaction, that will be picked up by a builder that actually has the correct access rights to these different chains. There's like an interesting kind of like balance going on there, which you probably can go like max value capture because you still want to have like the good user experience as well.
Right. Since we're talking about like bundle and MEV, I would just jump ahead to like here, right? Like an example of like how these cross-chain bundle will actually be executed would be something like this, where you have like, for example, a user will want to bridge ETH from L1 to L2 and swap on L2 and then bridge it back to L1. And let's say these are all atomic. They're supposed to execute together, right? So like within the builder's database, like he will like virtually see these bundles together, and then at the rollup point, right, he will have to he will have to roll up the transaction into L1 block with like the first transaction being on L1 and the second transaction on L2, the third transaction on L1 again. And then and this kind of like this implied that the builder has to have exclusive sequencing right of the L1 block and the L2 block, because like the order have to be preserved. This is where pre-confirmation comes into place, right? If the builder doesn't have the right through pre-confirmation if there's isn't like a pre-confirmation provider that let the builder to execute to become like a to guarantee the builder for execution pre-conf, then this thing wouldn't be possible. That's why pre-confirmation is also very, very important for us. However, though, like if you only care about like L2 order, like if the transaction itself doesn't go through L1 in a strictly orderly manner, then you don't have to have execution pre-confirmation. Like inclusion pre-confirmation will be enough if you just want to roll up the state of L2. However, if you want to introduce any synchronously any composability actually from L1 to L2, the fact that like the L2 execution depends on certain state of L1, then you do need like execution pre-confirmation. Yeah. So that's that. And in fact, if we want to go into like more detail into how these transactions are formatted, so this is our design, right? I like bundle these 3 transactions like this because it's like easy for people to understand. But in fact, for a user, you only need to like send 1 transaction that are being packed like onions that look like this. So the user, since this transaction is originated from L1, right? Because you bridge from L1 to L2, right? The outer skin of this onion will be like an L1 transaction in which the inner transaction will be encapsulated as, call data and being picked up by the L2 process within the base builder big node, the node that sequence for both L1 and L2, right? After the L1 is being processed from the L1 execution, like it will like call the L2 node, right? And sense the inner parts of the onions, and the L2 node get executed, which encapsulate another L1 call within itself that are being emulated in the L2 EVM, right? So at the rolled up time where we have to like roll up the end state to the L1, it will actually contains like 2 process, right? Like the L2 thing, the L2, the pink layer will actually be rolled down in the L2 execution context, but the L1 processes will be rolled up to as the end state of the L1. And everything has to be carried out in TE or ZK because you can't just like insert Merkle proof randomly in these processes, right? Like if everything is directly proven in real time, like the execution integrity is guaranteed, then you can basically like roll up and roll down freely at any time in however way that you want to compose your transaction. Yeah.
Yeah.
So
this is, and it's like embedded, right? Like we have transactions that are embedded into one another. My question here is like, everyone who's around and like using like Aave and Uniswap and Compound and like the popular applications, they had liquidity on L1, but now everyone has migrated their liquidity and their assets and they're doing things on L2. It sounds like here, L2s are still used for execution, but it's almost like we're going to like bridge to the L2, we're going to do some execution, and then we're going to come back to the L1. Do you think people are going to migrate liquidity back to L1 and then start to like use like L1 and make transactions and hold their assets on L1 and then use this to like make transactions on L2 and then get it back on L1? Or now that all the liquidity is away from L1, do you think it's just going to stay on L2s?
I think that's a good question because like I said, right, we're using L2 block space as a execution layer of L1. So like L2 is literally a execution extension of L1. Mm-hmm. And honestly, since L1 has the maximum amount of security guarantee, so it kind of makes sense to keep your assets on L1, right? And just leverage, because like by the end of the day, all these L2 nodes are just extra execution power, like execution capacity that you add on to like the base chain, like the base L1 chain, right? So I think like after this ecosystem being picked up, maybe you will see more people migrating their assets back to L1. and only use L2 as a execution layer, and then the L2 builder will get revenue from like processing your execution.
Yeah, so I think it's also like the very like depending on like kind of like your priorities, right? So if you are like very like security sensitive, or you have like you have like a lot of like funds on the L1, then you do start caring more like, okay, where is kind of like the most liquidity? Where do I actually have like the least like slippage on like the swap that I want to do? And then it makes sense to kind of like pay the extra cost to still have your funds on the L1, or like partially on L2, or whatever you want to kind of like do, and then pay this extra cost to have this. But for normal users that are like very cost sensitive and you want to just swap like $100 or whatever, then yeah, you do want to store your funds on the L2 as well. And then you kind of like have the benefit of like, if the liquidity on the L1 is still much higher than on the L2 that you're on, or like another L2, then you can still kind of like combine all these transactions in one, do like a single swap on the L1, and then get your funds back on the L2 with like the minimal slippage. So it opens up like a more like a design space of like different options, and it's kind of like up to you, kind of like what option do you want. Also the kind of like on the application level, like how can I scale my application? Because yeah, if you do still have your funds on the L1, or the application kind of like state is stored on that one, you do end up paying like a higher cost, right? So you will pay like a very kind of like expensive like asset store cost to actually store data there, or kind of like move funds between the L2 and on the L1 smart contract. So yeah, you do pay a cost. So it needs to be worthwhile to actually pay this cost, and it depends on whatever the user's kind of like priorities and like the app's priorities.
Got it. Cecilia, what else? Yeah, please go ahead.
Oh, I was gonna go for the next slide, but if you have any question, we can like answer.
No, my question was like if there was more slides, and like what else, are like some observations and consequences of this design.
Right. So this is like more details of the design, where if like a transaction is being initiated by L2, we can still like pack it up as like one transaction, but in this case, like we'll have like one transaction follow the other transaction, but still like encapsulate the L1 transaction that are in the middle. So like it's all about emulating L1 transaction while you're executing on L2, and then prove it later on. And then like the L2 sequencer will see like the pink transaction separately on layer 2. So these are the details, I guess. And I think this is very important. Like if we evolve how we did from L1 and L2 to like cross-chain transaction, we can do the same thing from like, for example, chain A and chain B, right? And I think Brad can go over this. It's like more like, I think like there's like details about on layer 2 only that are different from L1 to L2. Brad.
Well, I guess it's kind of like I think it's still pretty similar to the L1. But yeah, so kind of like if you do just like a transaction between the L2s, then basically you still have like a single transaction, and you would just directly call in the other L2 as well. But yeah, the difference here is maybe that, okay, there are kind of like these sub transactions that have to be, both validated by the prover, but also kind of like to split up the state between those two L2s, you kind of like have to have like this sub transaction that like the blue rollup actually has to execute, and then the pink stuff is actually being executed only by the pink rollup. So yeah, it's kind of like more of like a scalability kind of like a implementation detail, where for everybody, they only actually care about like the one transaction, also from the builder's perspective, but we do still to have like split them up just to make it possible to sync the specific nodes separately. So there's like no kind of like interdependency even for cross-chain transactions.
Right. So from a block building standpoint, if a builder sees this like pink layer 2 has a lot of traction, right, I can choose to sequence for the pink layer 2. Well, in this case, it should still have the access to the state of the blue layer 2. Is that true, Brecht?
For the builder, yeah.
Right. So like if you do want to maximize value capture from sequencing multiple layer 2, you will have to like obtain as much state access as possible. And then I think like the block building algorithm, you know how people like build block differently, like rsync or like beaver build or titan, they all have like different tactics in block building, right? And in this case, like all their tactics will be renewed, right? It will be very interesting how the block building space will evolve with this situation.
In this model, are all of these based rollups? The pink and the blue are both based?
Yes.
Okay. And so they use the same sequencer, and which is the L1 validators. And so wouldn't the L1 validators wouldn't the sequencer have access to the entire state of the pink and the blue? Or
not necessarily. So they would see all the transactions being posted for these L2s, but they don't necessarily keep the actual like L2 state derived from those transactions themselves. Well, I guess the L1 validator is like probably not doing anything in any case, but yeah, it's kind of like whoever kind of like gets the right to actually build the block for the L1 validator, would have to get sync the state.
They would have to get the state for both of these rollups.
Yeah. So on chain, so what the L1 actually only sees most of the time, especially for like the L1 case, is only like data, right? So they only see like data, and so to be able to get the state that you actually need to execute transactions for an L2, you actually have to take that data and like execute it on your L2 node. And that's kind of like a lot of work, because now, especially with like data blobs, the blob data, you can like put a lot of data there. The L1 validator doesn't have to actually do a lot of stuff with it, just have to propagate the data. They don't have to actually like compute stuff with it. And so that's the difference. So if you actually want to sync an L2 node, you actually have to take that data and actually execute on top of it.
So there's a difference in like syncing the L2 node, in between like syncing the L2 node and just like validating all of the blocks, right? Like for L1, it's still the same. Like the L1 validator still only sees this block, which is being proposed through the regular PBS, right? It's just like the stuff that the pink and blue transaction here it will just appears as like a regular rolled up transaction, right? And then a pink builder or like a blue builder or blue or a pink node that are specific to the chain will actually see this pink and blue block and execute these blocks locally, right? So like for L1, the pink part and the blue parts are agnostic. So it doesn't add any execution overhead for L1 validator or a builder that only want to build for the L1, right? You can basically just ignore the other things. It's totally optional for like these like pink or blue builders to build the whole thing. And it's also very like optional for like a pink builder that want to exclude the blue transaction. Then like the pink builder will just only build like this single transaction over here, right? Because this bundles also contains the blue, which means you also require the blue state.
Right.
Yeah.
Okay.
So it's totally open and competitive in that case, in that sense.
Right, because these builders are opting in to the blue or the pink or the blue and the pink.
Yes.
Okay. And so I guess to finish off like this podcast, which has been absolutely phenomenal, I want to ask a really, really dumb question, which I think I know the answer, but maybe it'll help just to like kind of like revisit the basics. Can you guys like, what is the difference between a builder and a sequencer?
Welcome aboard on our journey into the singularity. This is the endgame roadmap for Frax and Fractal, the new L2 out of the Frax ecosystem that is totally based on fractal scaling. Fractal is a modular L2 blockchain built by Frax with modular and fractal scaling in mind. Fractal scaling is based on the Mandelbrot set of fractal images, and it explains how L2s become L3s and the entire app chain lifecycle goes through its evolution. The Frax ecosystem is made of some of the top builders in the space and has stemmed from its OG days of the Frax stablecoin It is now in the LST space, the LRT space, and this Fractal L2 joins the existing suite of Frax products, including Frax Swap and Frax Lend. You can see Frax Ferry, the bridge to go from any chain, Arbitrum, Optimism, or mainnet into the Fractal mainnet, bridge your tokens, and bring your Frax assets into the Fractal ecosystem. Join today to get the best out of Fractal. You are still early. Join today, take part in our expedition into the singularity.
Everclear is pioneering the clearing layer. The clearing layer can almost be thought of as splitwise when you go on a trip with friends, but for the blockchain. What I mean by that is when users are sending cross-chain messages, there's oftentimes fillers and solvers who have balances left on different chains that they need to rebalance and reset their positions. This is where Everclear comes in. Everclear is pioneering a collaborative approach to the chain abstraction future, and they are willing to work with interoperability partners, solvers, and other providers in the space to build a interoperable and chain abstraction future. Check out Everclear at everclear.org, and welcome back to the Rollup.
Okay, the definitions game. Sequencing, I guess, only the determines the order of the transactions, and I guess the builder would actually build a block out of it. I think that's kind of like how I would define them, but I am sure people will disagree or like have other definitions on them. But yeah, I guess.
Okay. So
now like the trend is to modularize sequencing and block building, or specifically data posting for Rollup, right? Like for example, we just got to know from like Paradigm's Frontier event how like Optimism is doing their Rollup and their the ZK fraud proof thing. So like their stack is actually super modular, right?
Mm-hmm.
You have like a share sequencer that just only responsible for like sequencing the order of transaction. That like the data, even the data availability doesn't really matter. You literally need to just like label the sequence. That's it. And then like they post the DA later on when there's like enough transaction to fill up a blob, because they compress their blob very tightly to save cost, right? So, and then like in order to execute a optimism state, you actually need all of the data availability. So that's when the builder comes in to build a block. Building the block meaning execute out of a transaction. But sequencing literally just mean, you have a bunch of transactions. You actually don't care what is the result. You just sequence them randomly. But like as a builder, as a node that actually want to profit from sequencing the transaction, you do want to actually build the block, meaning execute a block to see how much money you will earn.
Mm-hmm.
So that's building and sequencing.
Got it.
Yeah.
Okay. So in terms of this pink and the blue, would it be fair to say that like the sequencer is almost like, in the pink and the blue, they're kind of the same thing. Like they're the ones that are like embedding the rollups or embedding the transactions in this bubble, and then the sequencer kind of like sequences the 1, the 2, the 3, and then the builder is the container on the left that says, okay, now we have these 3 transactions in sequence. We're going to process these transactions on the L1 and build the L1 block made up out of these transactions.
Not exactly, because the user send these transactions as a whole onion, or in this case a snowman, right?
Okay.
Like
Mm-hmm.
the whole thing will be like, so for it wouldn't make sense for a user to split up like 3 different transactions and make a sandwich or whatever, and send it to the builder, like, because we want to have like a good UX,
Mm-hmm.
right? The user should just be able to like specify intent or whatever that basically does these 3 things, and then like the UX will package them as like an encapsulated transaction and send it to like, and put it in the public mempool. And the builder will see like, okay, so this transaction will require me to have the pink state and the blue state. And okay, and I only have the pink state, so I'm probably not supposed to touch this transaction. I should probably leave it to someone else.
A different builder that has access to both the state.
Exactly. And that also means that I'm probably not profiting from this transaction.
Right.
But go ahead.
Well, can two builders coordinate with one another? Like if I have the pink state, you have the blue state, can we build this block together?
I mean, by seeing coordination, if I want to have the state access to the blue state, then like I'll probably need the database to be already there available for me. That basically just means I do have the blue state. You know what I mean? So like you can't just like send people your entire database for some other rollup because it doesn't work like that.
Okay.
Well, you could send like the data that's being touched, but yeah, I guess the cost you pay then is latency. So it would like well, depending on the latency between those two builders, it could be feasible or not. But yeah, it would slow down the block building process like substantially. So if you kind of like want to optimize, kind of like do like lots of like different variations of the block, this could be not ideal. But if you do something like pre-confirmations, but like first in first out, then like the ordering is kind of like simple. So you just do the transactions as they come in. So then the extra latency could be acceptable, except that you also kind of like enlarge kind of like the time until the pre-confirmation can also be returned. But yeah, it is possible. It just depends on like what's kind of like the latency kind of like tolerance in kind of like your block building process.
Yeah, because like in a developer standpoint, like having the state literally means having an active in-memory DB, in-memory BD for like a chain, right? So if you don't have a BD process running on your laptop, that basically means you don't have the state. You can ask for other people for like the Merkle proof of some random state, but that's like not how you would run your software.
Yeah, and I guess from a user perspective, like I'm not going to know if there's a builder out there that has access to both the states that I'm looking to transact on. And
yeah.
And so
like
does that prohibit like certain transaction types, or it would just kind of like get higher latency as a result of the block builders having to like finalize on one chain and then going in asynchronously on another chain?
Well, not really, because you as a user, you just throw your transaction in the mempool, in the public mempool, and hope for the best, right? If you're touching a chain that is like super unpopular, no one picks you up,
right? And
you just have to, right? And it's like the same scenario for the L1 today, right? If you're throwing a transaction in the mempool that has like no tip and consumes a lot of gas, you probably can't hope for the best. You know what I mean?
You won't get it executed, especially not quickly.
No. Yeah.
And I guess because if you have like funds on like one of these unpopular chains, then it would be bad, right? Because that would mean like your funds could be like stuck on this kind of like very unpopular rollup. So that's why it's also like important that we are still like based. So if nobody actually wants to move your funds out, then in the worst case scenario, you can just do it yourself. You can propose your block yourself and still recover your funds.
Wow. Got it. Okay. Very cool. I mean,
yeah. It's kind of like a service. Yeah, like block building is kind of like a service that these builders kind of provide you. In the worst case scenario, you just do it yourself.
Right. And for the large, like the subset of chains that have a large amount of liquidity, it makes sense that these block builders are going to have access to the state for these prominent chains. But once you start getting exotic about the different types of chains that you're going and interacting with, you can't really make the assumption that block builders have access to all of that state. And so they might not pick up these transactions. But for all of the rollups that do have a large amount of liquidity, block builders have access to the state, then we can make a pretty safe assumption that if I'm doing a cross rollup transaction amongst these rollups, then I'm going to be able to execute kind of like this onion type of transaction bundle across those rollups, because builders like one builder has access to all the state of all of those rollups.
Yeah.
And And it's also not that it's like very expensive to actually sync a node, right? So that's kind of like the thing. These nodes should actually be like pretty, normal Ethereum kind of like scalability level. So you can just run them on like pretty standard hardware. So it's not a big extra cost for builders to actually sync like a lot of the L2s.
Got it.
Right.
Got it.
And like everything will be like incentivized, right? Like user will be incentivized to move to a more prominent chain. And the chain will be incentivized to become more prominent so that more builders are willing to build for them.
Mm-hmm.
But also, however, a caveat would be if a chain becomes too congested, right? You have base fee spiking up, then it's also like incentivizing people to move off from your chain due to congestion. So like it is like a very dynamic scaling solution, I would say.
Mm-hmm. It's a big game of hot potato.
Yes.
Awesome. I really appreciate you guys sticking around past the time and really going deep into this design. I think this is something that, we're big proponents of base rollups. I think to see this play out is going to be fascinating. So yeah, thank you for taking the time to explain it.
Glad to do it.
Thanks for having us.
Awesome. Do you all have any closing thoughts like that you want to share that you feel like maybe we didn't cover, or anything else that you want to say?
I basically said everything that I wanted to say. Like I'm just like super excited to see like this ecosystem being built, like how everything will unroll itself, especially with the builders, right? Because like people are talking about MEV all the time, and then it's a very sexy idea to revenue from people's transaction, bundling, sandwich, and all that stuff. And we really, if this kicks off, like it really unbundles like a new model for like how do you revenue on chain and how like app chains would play out on those things.
Yeah.
Yeah, also I guess there is some challenges, some sexy and unsexy challenges, because the system kind of like you can work great, but I guess there's some kind of like some not unsolved problems, it's like unclear kind of like how things will actually work out. So obviously the fast kind of like finality that we need, the real time proving, the security kind of like considerations about that. We have like some plans to do that, but I guess there's some implementation details that are pretty important to actually make sure that the system actually works. Also kind of like the synchronous composability with the L1 is kind of like a tricky thing to do, so it might not always be available. But I think like as things progress and these things actually kind of like pick up, then we should be able to actually synchronously compose with the L1 most of the blocks. And I guess one of the main benefits there that might be like not so sexy is kind of like just the simplicity of things. So you can say like, okay, when will this kind of like synchronous composability with the L1 be used? There's kind of like limited maybe use cases depending on the application, but still having like an in protocol kind of like solution for this that is also like uniform across kind of like all the different chains that you want to access, I think is kind of like a very important thing to keep both the security high and kind of like the simplicity like also like very high for users. So they don't have to really care about like which chain they're like accessing. And they also don't have to care too much about like the specific implementations of kind of like bridging between L1, L2, these different L2s, because the functionality is directly implemented in the L2 kind of like system itself. So I think that's also kind of like a big benefit of doing things like this, because now, you have like bridge smart contracts, which have pretty complicated code to actually make this bridging possible. We kind of like just make like a very kind of like a generalized solution. We build it into a node, and then the application can just depend on that.
Yeah. And this is solving the fragmentation problem at a very, very base level, which hopefully, fixes kind of like the interoperability and fragmentation, and then standardizes it so that everyone can build on top without having to really worry about fragmentation going forward.
Yep. In the best case scenario, that's what we're aiming for.
Cool. Awesome, guys. Thank you so much for coming on. And very much looking forward to doing this again soon.
Yep. Thanks a lot.
Thank you.
Bye.
Bye.